So you've probably seen something like this in the past 5 presentations, but I'm going to walk through kind of the basics of what is fully homomorphic encryption. Well, it's encryption, and you can turn an FHE scheme into a public key scheme, as we saw in the LWE presentation. But FHE has these additional magic properties whereby you can add or multiply 2 ciphertexts together, and this will produce a new ciphertext that contains the sum or product, respectively, of the constituent operands. And once you can do addition and multiplication, you can evaluate polynomials, and once you can evaluate polynomials, you can do Lagrange interpolation, and once you can do that, you can compute anything you want. So to give you a timeline of the development of FHE over the decades, it was first conceived in the late 70s, and it took about 30 years for the first FHE scheme that was actually realizable to come into fruition. That was Craig Gentry in 2009, where he proposed the idea of bootstrapping, which you just heard about in the last presentation. And the idea is you're trying to reduce the noise in ciphertext, and this allows you to keep computing so you can compute arbitrary functions. Then a few years later, we got BGV and BFV. You've probably seen the BFV scheme earlier today. These schemes allow for fast arithmetic over polynomials, but unfortunately, bootstrapping under these schemes is very slow and is typically not done as a result. And then a few years later, we got CKKS and TFHE. And CKKS is even faster at arithmetic than BGB or BFE, but the arithmetic is approximate. And we also got the TFHE scheme, which supports extremely fast bootstrapping. And so newer is always better, right? Well, the answer is you want to choose the scheme depending on what you're trying to accomplish. If you need to do lots of arithmetic, then BFE is going to be a better scheme. But if you need to do comparison operations and kind of more complex like things that require bit twiddling, TFHE is going to be a better scheme. And the 2 schemes highlighted in yellow are the ones probably most interesting to us in Web3. So CKKS is again approximate, and BGV has these modulo switching operations that are kind of unwieldy to propagate and work with data. So what can you do with FHE? Well, you can have private orders and auctions. You can do DAO voting. And with DAO voting, you can implement this with a ZKP, but you typically need some kind of commit and reveal process. And it requires several interactions with the chain. DAO voting, on the other hand, using FHE, you can have everyone just simply submit their vote. You homomorphically compute the result, then you can decrypt the result of the vote and then reveal that to everyone. And so nobody's vote ever gets revealed, and you can do it with fewer chain interactions. You can also do private inferences. So I can encrypt some data, send it off somewhere. They can run a machine learning model on it, send me back an encrypted result that I can decrypt. And you can also do data analytics and things like that. OK, so what do you have to do to deploy FHE? Well, it has a lot in common, actually, with ZKPs. So with ZKPs, you need to choose the scheme you're going to use depending on what kind of prover times you need, what kind of verifier times you require, how big of proof sizes can you tolerate, do you need recursion, can you handle trusted setup or not? These are all kinds of different trade-offs. With fully homomorphic encryption, you similarly need to pick the appropriate FHE scheme depending on what you're trying to do. So as I mentioned before, if you need to do just raw addition, multiplication kinds of things, BFE is probably a better scheme. TFHE is going to be better if you need comparisons and things like that. They also have subtly different like key sizes and ciphertext sizes. So once you have chosen which scheme you're going to use, you then need to build a circuit with it. In ZK land, you would use error constraints or R1CS or something like that. In FHE, you build a circuit specific to the scheme you're using. So in BFE, you're going to have basically multiply and addition gates. In TFHE, you have these programmable bootstrap gates that perform bit operations. But FHE has this other kind of concept that there's no real analogy for in zero-knowledge proofs, whereby you have to choose your parameters efficiently, or so that your computation runs efficiently. If you choose parameters that are too small, then you will get the wrong answer when you run your computation, or you'll be insecure. And if you choose parameters that are too large, then you are going to spend a very long time computing your answer. So working with FHE today, you kind of have to be an expert in it to really use it efficiently. And so FHE has performance problems. If you are going to perform some computation homomorphically versus doing it natively on your processor, you're looking at between a 4 and a 6 order of magnitude slowdown. You are more on the lower end if you're using batching. You're on the higher end if you're not. And the parameters that I previously mentioned, the performance is highly sensitive to this, so you really have to get those right. And then circuits are, if you're a hardware developer, a thing you're probably used to working with, but most developers are used to working with for loops and if statements and things like that. FHE also has a number of usability problems. So your plain text in the BFE scheme, for example, is a polynomial, and you have to do things like, if you want to use integers, you have to trick a polynomial into behaving like an integer. And so you have to use an encoder to accomplish that. And finally, FHE has these kind of new operations that are scheme specific, and you have to know when to use them effectively. So for example, in BFE, there's an operation called relinearization, which you have to use after doing a multiplication at some point. And there's also bootstrapping operations, and you have to know where to insert those. So can a compiler make FHE easier to use? And the answer is yes, but it's going to depend on what application you're trying to develop. So we actually built an FHE compiler. We currently support the BFE scheme, but we're looking in the next few months to add TFHE support. And the kind of idea of how this works is you just write a standard function in Rust, and you put a little macro on it, and then our compiler can go and turn that into a circuit. The compiler will then also choose parameters for you that efficiently run your circuit, or that efficiently run it, and guarantee that the answer you get out is correct. And once you have a circuit, circuits are directed graphs, and so you can actually parallelize execution down this graph. So our runtime will automatically parallelize your program for you. And this is what an FHE program looks like in Sunscreen. I don't know how many lines this would be in Seal, but it would be a lot. So what we have here is our hello world. We want to multiply two values together, A and B. So I denote that A and B are encrypted integers. And I can compile this by invoking our compiler, which produces an app. An app is a bundle of circuits, so you can actually have multiple FHE programs. You can then compile, or once you've compiled your circuit, you can create a runtime using the parameters that our compiler found. Then once you have a runtime, you can generate a public-private key pair. You can encrypt the value 15 and 5. And then we run our program, multiply A and B together, so 15 times 5, which we can decrypt and see that the value we get is 75. So that's kind of what it looks like in our compiler. We're not the first FHE compiler to exist, but a lot of compilers give up a huge amount in performance. So we're taking this chi-squared test that came out of this SOK paper, and we're going to time key generation, encryption, decryption, and computation. And we're going to run it on a pretty vanilla AWS machine, 8 cores. And if you were to manually implement this in the BFE encryption scheme with Seal, you would take about 50 milliseconds to run this. But we see that many of the compilers have hundreds to thousands X overhead in runtime. And there's two notable exceptions, one of which is Ava, which is built on the CKKS scheme. So again, probably, unfortunately, not interesting to a lot of Web3 applications, but Sunscreen only has a 1.3x overhead. So what remains? Now that we have a circuit, you need to deploy it and run it somewhere. Is this going to be on-chain? Are you going to have a rollup that can demonstrate that it has run an FHE computation correctly? Doing this is actually an active area of research, and it's currently very expensive. You need zero-knowledge proofs along with FHE. So if I want to send you money, I have to prove that the amount I'm sending you is greater than 0 and less than my balance. I also have to prove that it's a valid encryption under the correct key. And then finally, we can move from single key to threshold FHE, and this will enable like additional applications. But so you have to take all the complexity of single key FHE, and now you have to add like a new trust model. You have to think about the network communication overhead of doing the threshold decryption. So there's a whole lot of new additional aspects that you have to think about with threshold. So we actually have two different experiences if you want to go and play with FHE today. We have on the left our playground where you can go and write and run FHE programs in your web browser. Our Sunscreen is just a Rust crate, so there's no external tooling required. And so you can then take this, go and create a Rust project and use the Sunscreen crate and just pick up where you left off. And on the right, we have an auction running homomorphically. So you can encrypt a bid, and it will go and you'll go against a bunch of like simulated competitors. And the auction runs, and then the only thing that's revealed is who the winner was. All right. And I think this is the last slide, so I'll take any questions.
Or compiler to automatically choose the parameters like of BFV. So the question is that now BFV is not that for the homomorphic, it's level homomorphic. So the parameter depends on the applications, right? So essentially it depends on the number of modifications. So how do your compilers to choose the parameter?
Yeah, so there's two different ways you can do it. One is you can have a noise model. So you can say an add gate produces this much noise, a multiply produces this much, and then you can kind of predict the failure rate based on that at the outputs. But what we actually do is run your circuit, measure the noise, and just kind of empirically discover from that what your parameters should be.
I wanted to ask about representing general data types in Rust, where you have, like U32, U64. Mm-hmm. Do you all map them all to finite field elements? Or like how do you all handle those?
So if we go way back to here, you see that we have this cipher of signed. Okay. Signed is implements the FHE type trait. So any type you have to implement that trait. Okay. And only if you have to be able to encode whatever you're trying to do onto a polynomial or more than one polynomial.
For sure.
So that's kind of the trick. You can create your own types, but it's not trivial.
Gotcha.
And but these are not 64-bit integers. They're like 4,000-bit integers.
Wow.
So.
That's really cool. Thank you.